All right, verifying trig identities. This is one of the tougher sections in your trig classes. I've broken down these problems into 4 steps. If you follow these steps in this order, it should cover and solve about 98% of these problems that you're going to encounter. Now, these problems are designed in a specific way unless your class specifically says otherwise. You want to solve these problems by turning one side of the equation into the other side. You don't want to be moving terms onto both sides of the equation. Typically, you take the left side and you turn it into the right side to verify that the identity is true. Now, for our steps, number 1, factor out any common factors. If you look at your problem and there's no common factors you can factor out, then you see if there's any trig substitutions you can make with the Pythagorean identities. Over here on the right, we have the Pythagorean identities written. If you memorize the first one, you can always derive the other two. Sine squared plus cosine squared equals 1. If I divide each of these terms by cosine squared, I will get this second equation. If I divide each of these terms by sine squared, I will get this third equation. So with this step, number 2, you're just looking to see if there's any substitution you can make that will simplify your problem. And I'll show you an example with that. Third, if you do either of these or you don't do either of these, you always then look to combine fractions with a common denominator. Now, this is sort of like a special scenario you'll run into. You're basically just going to see this in very specific types of problems, and we'll go over one so that you'll see what I'm talking about. Now, if you go through all these steps and you're unable to accomplish any of them, your fail-safe is always to then rewrite every term in sine or cosine form. Now, all 6 of the trig functions can be written in terms of sine and cosine. This is always what you're going to revert to if none of these are solving anything for you. Once you rewrite them, you come back to step 1 and repeat from the top. Okay? So, our first example we're going to look at has both steps 1 and 2 incorporated in it. You're going to see in this first example here on the left, we can factor out a secant squared x from each of these terms. So I'm going to take out secant squared x like this, and I'll be left with secant squared x minus 1. I'm not going to keep rewriting the right side. Just know that the right side stays exactly as it is until we've turned the left side into it. And then we'll put a check mark and be done with our problem. Now, we factored out secant squared x. Well, remember, our next step is to see if we can utilize a trig substitution. So, if we look at this second equation here, you will notice if I subtract 1 over to this side, it will then look like this. So secant squared x minus 1 is equivalent to tan squared x. So I'm going to keep my secant squared x in front, but then in these parentheses, instead of secant squared x minus 1, I'm going to write tan squared x. All right, we're getting there. Now, here's where you basically, either intuitively, you're going to know to do this right here, or even if you're not at that spot yet, as we go through these steps, you'll go, well, I can't do any of 1, 2, and 3 here. So naturally, I should rewrite everything in terms of sine and cosine. 1 over cosine squared x times sine squared x over cosine squared x. Now, as I look at this, I'm going, well, this doesn't really get me anywhere to where I'm looking at what I have over here. So sometimes this is going to happen in these problems where you might need to reassess and sort of back up and go, okay, I got to remember my goal here is to turn this side into this side, okay? Now, where this problem gets unlocked is actually back at the step where we made our trig substitutions. Here, you'll notice secant squared x, remember, secant squared x itself is equal to tan squared x plus 1. So, you'll notice if I sub in tan squared x plus 1 for secant squared x here, times tan squared x, whoops, ugly, times tan squared x, and then I distribute the tan squared x onto these terms, well, voila, look what we end up getting. Tan to the 4th x plus tan squared x, and that exactly equals what we wanted to turn it into. Now, yes, I have these terms written in a different order. That doesn't matter. Remember, when you're adding two terms together, it doesn't matter the order that we write them in. So, yes, we've verified these identities here. All right, so this problem incorporates step 3. It's usually very obvious when you want to do this step because you're going to have two fractions and they're going to have different denominators. So that's almost always calling you to combine those fractions with a common denominator. I mean, I almost can't think of any problem that is set up in this structure where you wouldn't do that, to be honest. So each of these needs the same denominator, so I'm going to have to multiply this first fraction by tan x on top and bottom, and I'm going to have to multiply this second fraction by 1 plus secant x on top and bottom. So that's going to end up looking like tan squared x over tan x times 1 plus secant x. And this is actually a key point to make here. I always recommend on these type of problems, you don't yet distribute out your denominator. Wait a couple of steps before you go and do that, because what often happens on these problems is one of these terms in your denominator gets canceled by something in the numerator, and that's actually what's going to end up happening on this problem, you'll see. So hold off on distributing this until you know that that is not going to happen, okay? On our second term, we're going to have 1 plus secant x times itself, so I'm going to write that as squared. And of course, we're going to have the same denominator on this one, 1 plus secant x. Okay, so when we're looking at this, we might think, okay, do I want to do a trig substitution with a Pythagorean identity? Typically, you want to go from more complex to more simple. So I wouldn't necessarily want to take tan squared x and change that to secant squared x minus 1, unless it's like the last problem we saw where that clearly was going to be beneficial for us. When we look at what we're trying to change this into, there's really nothing that jumps out at us as that being a beneficial move to make. Now, when you have something squared like this, you're probably going to want to FOIL that out and see what that gets you and see if that helps you progress. So we're going to jump to having these combined all as one fraction. Okay, so we know our denominator now is tan x times 1 plus secant x. Now, when I FOIL this out, I guess I can do it up here real quick just for you guys to see. 1 plus secant x times itself. right? So we're gonna go this term times this term. We're gonna get 1 plus secant x plus secant x, that's plus 2 secant x plus secant squared x. Okay, so that's what's gonna go here. We got plus 1 plus 2 secant x plus secant squared x. Now, here's where the Pythagorean identity gets used. Look at this right here. Right here we have tan squared x plus 1 that we can write simpler as secant squared x. And it also should intuitively make sense, because if I do that, I'm going to be able to combine some like terms in my numerator, and now we're getting somewhere. So this turns into secant squared x plus 2 secant x plus secant squared x all over, I guess I'll just keep writing the denominator out for continuity. Okay, now what's secant squared x plus secant squared x? 2 secant squared x plus 2 secant x, still over tan x times 1 plus secant x. So now, again, if you're just going back through the steps, it's like, okay, what can I do now? Now I'm able to factor out a common term in my numerator. I can factor out a 2 secant x, and I'm left with secant x on this first term, and I'm just left with 1 on the second term. Remember, whenever you factor something out, you need to be able to put it back in and get exactly what you had before. And that's the case here. So this is over tan x times 1 plus secant x, and look what happens. Boom, boom. These cancel. Secant x plus 1 is the same thing as 1 plus secant x. They're both being multiplied by something, so therefore they cancel. So all we're left with is 2 secant x over tan x. And I would pretty much just say, okay, this is 2 secant x times cotan x, which then I would say is 2 over cosine x times cosine x over sine x. Boom, boom. We're left with 2 over sine x, which is 2 cosecant 2 cosecant x. Voila. That was what we were trying to turn it into here. So there's that one. All right, so here's our sort of special scenario where you're going to want to multiply by the conjugate. And again, these problems are kind of obvious. They're kind of calling you to do it. Whenever you see 1 minus just a single term like sine x or cosine x or secant x, or 1 plus cosine x, sine x, something like that, you're going to multiply by the conjugate on top and bottom. So in this case, we're going to multiply by 1 plus cosine x on the top and the bottom. And there's a reason that we're doing this. The reason is because our denominator now, we can FOIL it out, right? This is like in parentheses. So our denominator ends up becoming 1 minus cosine squared x, which if you look at your Pythagorean identities, this is equivalent to sine squared x. So in our numerator, we end up with, and again, I would just wait like at least one step before you go and you distribute the other side of your fraction. Just like hold off a second and see if maybe something's going to cancel, which of course, again, on this problem, that happens because in our numerator, we have this And in our denominator, we have sine squared x. So this sine x cancels with one of these sine x's. So that goes away, and the 2 essentially just becomes a 1, and we're left with just sine x. So now we have 1 plus cosine x all over sine x. And you always sort of have your eye on what you're trying to turn it into. And we can tell now that if we split up this numerator, right, I'll have 1 over sine x plus cosine x over sine x. Well, that ends up being cosecant x plus cotan x, and that equals cosecant x plus cotan x. Check. So that's that problem.